A single photon just appeared to travel backward in time by 27 nanoseconds. A 2023 experiment at the University of Toronto confirmed this quantum time reversal. But your brain's arrow of time still only moves forward. The second law of thermodynamics says entropy always increases. This new study suggests that, under the right conditions, cause and effect can swap places. An egg scrambles, never unscrambles. A sandcastle collapses. Time, by this logic, only flows in one direction. The entire experiment cost less than a used car. No underground collider spanning borders. Just a laser, a tabletop device that challenged the arrow of time itself. But at the quantum level, the fundamental equations of physics are time-symmetric. Newton's laws, Maxwell's equations, Schrödinger's equation, none of them care which direction time travels. If the microscopic laws of reality are reversible, why does time only move forward for us? This is the problem a team of researchers decided to tackle. The experiment was deceptively simple. They fired a single photon. In classical physics, the photon would either pass through or reflect. But quantum mechanics is not classical physics. Instead of committing to one path, it entered a superposition of both possibilities. The team then applied a second operation, a kind of quantum undo button. Its timeline effectively rewound. It is not a metaphor. The photon's quantum state was restored to what it was before it ever encountered the beam splitter. In a very real sense, the particle experienced a localized reversal of time. Now comes the central question. Does this mean time itself can be reversed? Or is something else happening, something that forces us to rethink what time even means at the quantum scale? It is the most empirically robust law in physics. It has never been violated in any macroscopic system. But here is the catch. The second law is a statistical law. When you have a single photon, the statistics collapse. The law does not apply in the same way. A single particle can fluctuate. It can, in principle, reverse its own entropy. This is what the experiment demonstrated. The photon did not violate thermodynamics. It exploited a loophole that only exists at the quantum scale. It is an emergent property of large systems. At the smallest scales, time is symmetrical. It flows both ways. This idea has been theorized for decades. The equations of quantum mechanics have always allowed for time reversal. This experiment turned a mathematical possibility into a physical reality. The implications are staggering. If time can be reversed for one particle, what about a molecule? What about a virus? The second law reasserts itself as systems grow larger. The probability of spontaneous reversal drops exponentially with each additional particle. For a human being, the probability is effectively zero. You will never unburn a piece of toast, but the fact that it is possible at all changes how we think about time. Time is not a river flowing inexorably forward. A preference for disorder, not a law. The universe does not forbid time from going backward. It just makes it astronomically unlikely for anything larger than a photon. They revealed a crack in our understanding of it. The arrow of time is real, but it is not absolute. It is a rule of thumb written by the universe for large objects. A language where time has no preferred direction. And that is when the real scientific puzzle emerged. The second law of thermodynamics is not merely a useful observation. It is the only law of physics that draws a sharp, irreversible line between past and future. Rudolf Clausius, a German physicist, first formulated this law in the 1850s. He introduced the concept of entropy. In any closed system, Clausius declared, entropy never decreases. This single statement has never been violated in any macroscopic experiment. Consider the egg. A fresh egg has a specific structure, a yolk suspended in white, encased in a shell. Crack it into a hot pan, and the proteins denature. The structure collapses. You cannot apply heat to the omelet and recover the original egg. This is not because the laws of physics forbid it on a microscopic level. It is because the number of possible disordered states for the molecules is astronomically larger than the number of ordered states. The universe, left to its own devices, always moves toward higher probability. This asymmetry defines every moment of your conscious experience. You can break a glass but not unbreak it. The arrow of time, as the physicist Arthur Eddington named it in 1927, is the psychological and thermodynamic directionality that governs our entire existence. Cause and effect would lose their meaning. Ludwig Boltzmann, the Austrian physicist who died by his own hand in 1906, understood this better than anyone. They rejected his statistical interpretation of entropy because it implied that the universe was probabilistic, not deterministic. Boltzmann argued that entropy increases simply because there are vastly more ways for particles to be arranged in a disordered state. Imagine shuffling a deck of cards. There are 80 unvigintillion possible arrangements. Only one of those arrangements is the exact order of a brand new deck. The probability of shuffling into that perfect order. The second law is not a cosmic policeman enforcing order. But here is the problem that Boltzmann himself recognized. The microscopic laws of physics are entirely indifferent to this arrow. Newton's laws of motion work identically whether time runs forward or backward. If you film a billiard ball collision and play the film in reverse, Maxwell's equations for electromagnetism are time-reversal symmetric. Schrödinger's equation, if you take the mathematical solution and replace t with minus t, the equation still holds. This creates a deep and unresolved paradox. If the building blocks of reality are time-symmetric, why does the macroscopic arrow exist at all? It is one of the deepest unsolved problems in theoretical physics. The measurement problem in quantum mechanics. When a quantum particle is not being observed, it evolves according to the Schrödinger equation, smoothly, deterministically, but the moment you measure it, the wave function collapses. The particle picks one definite state. You cannot undo a measurement. You cannot reconstruct the original superposition. The act of observation appears to break time-reversal symmetry. Some, like the Copenhagen interpretation often associated with Niels Bohr, argue that the collapse is a fundamental feature of reality, though Bohr himself viewed the wave function as a symbolic tool rather than a physical entity that collapses. Neither side has fully resolved the paradox. The arrow of time remains stubbornly unexplained by the fundamental equations. This brings us back to the photon on the beam splitter. If the arrow of time were truly fundamental and absolute, the photon should have committed to one path, scattered, and moved forward in time like everything else. The team demonstrated that a single quantum system could, with probability, reverse its own evolution. The photon returned to its original state. This does not mean the second law is wrong. It means the second law is a statistical law that applies to large systems. For a single photon, the statistics are different. It is 50% in this specific experiment. The arrow of time is not a fundamental force. It is an emergent phenomenon, a property that arises only when you have enormous numbers of particles interacting. It is real for planets and stars, but at the quantum scale, it wavers. It sometimes points backward. The experiment forces us to confront a deeply uncomfortable possibility. It may be a feature of our perspective. We experience time moving forward. A photon experiences no such constraint. Past and future may be indistinguishable. The experiment is a single study published in a single journal on a single particle. It does not overturn thermodynamics, but it opens a door that theoretical physics has been knocking on for over a century. If the arrow of time is not fundamental, then what is? What is time, if not the irreversible flow from past to future? Let us walk through the actual architecture of the experiment. It begins with a single photon and a device called a beam splitter. A beam splitter is, in its simplest form, a half-silvered mirror. It is a pane of glass coated with a layer of metal so thin that it is only partially reflective. When a photon strikes this surface, the laws of classical optics say it has a 50% chance of passing through, but quantum mechanics does not play coin flips the way we do. In the classical world, the outcome is determined the moment the photon hits the surface. It enters what physicists call a superposition of both paths. It takes neither path and both paths at once. The photon's quantum state becomes a combination of two possibilities. This is not a metaphor. This is the mathematical reality described by the Schrödinger equation. The researchers did not simply fire a photon at a beam splitter and watch what happened. They added a second critical step. After the photon passed through the beam splitter and entered its superposition of paths, this operation was carefully designed to reverse the effect of the beam splitter. Think of it as a quantum eraser that does not delete information. Imagine you write a sentence on a piece of paper. Then you take that paper, crumple it. Under normal circumstances, you cannot uncrumple the paper and recover the original sentence. But if you had a perfect record of every fold and crease, the researchers did something analogous with the photon. They had a complete mathematical description of the photon's state before it hit the beam splitter. They knew the exact transformation the beam splitter applied. By applying the inverse transformation after the photon emerged, the 50% probability is not a limitation of the experiment. The beam splitter creates a superposition of two paths. The inverse operation can only succeed if the photon is in the correct superposition at the right moment. Half the time, the quantum dice roll in your favor. The researchers did not control which outcome occurred. This is where the billiards analogy becomes indispensable. Imagine a cue ball striking a perfectly arranged rack of billiard balls. The balls scatter across the table in a complex pattern of collisions and trajectories. Under the laws of classical mechanics, you cannot run the film backward and expect the balls to spontaneously reassemble into the rack formation. The probability of the reverse process happening by chance is effectively zero. You roll it across the table, it hits a single obstacle, a small bump or a rail, and bounces off at an angle. In this case, the reverse process is not only possible but predictable. If you know the exact angle of the bounce, the ball can be unscattered because the system is simple enough that the full information about its past state is preserved. The beam splitter is the obstacle. The photon's superposition is the bounce. The inverse operation is the mathematical formula that reconstructs the original trajectory. The system is so small, it remains encoded in the quantum state. The researchers simply read that information. This does not violate causality in any meaningful sense. The photon was not sent back in time to before the experiment began. It did not arrive at the laser before it was emitted. It did not cause its own creation in a grandfather paradox loop. What happened is far more subtle. The photon's quantum state was returned to an earlier configuration. The photon itself continued to exist in the forward flow of time. Its state, however, the arrow of time for the photon's internal degrees of freedom, briefly pointed backward, while the photon itself continued moving forward through space-time. Time reversal in quantum mechanics does not mean traveling backward through time like a character in a science fiction novel. The system can be returned to a previous state without violating any fundamental law. It simply forgot the past in a very specific way. The study was published in Optica. The experimental design was elegant in its simplicity. No exotic materials. The entire setup could fit on a standard laboratory optical table. This is the kind of experiment that would have delighted Richard Feynman, a tabletop demonstration that challenges our deepest assumptions. The replication confirmed the core result. A single photon can, with 50% probability, be returned to its original state after passing through a beam splitter. Some physicists argue that the experiment does not demonstrate time reversal at all. They contend that it simply demonstrates a well-understood property of quantum superposition, that a quantum state can be manipulated and restored without any violation of thermodynamics. Others insist that the experiment reveals something deeper, that the arrow of time is not a fundamental feature of quantum mechanics. If time reversal is possible for single particles, the question becomes, at what scale does the arrow of time become irreversible? This is the measurement problem in a new guise. It is the same paradox that has haunted quantum mechanics since its inception. The experiment does not solve the paradox. It forces us to confront the uncomfortable possibility that time itself may be a statistical illusion, a consequence of our inability to track the quantum states of trillions of particles simultaneously. They claimed something far more modest and far more profound. They demonstrated that the fundamental equations of quantum mechanics are not just mathematically time-symmetric. They are operationally time-symmetric. The reversibility is not a theoretical abstraction. It is a physical reality that can be observed and measured in a laboratory. The universe, at its smallest scale, does not care which direction time travels. The second law of thermodynamics is not violated by this experiment. This is the crucial distinction that separates genuine scientific breakthrough from pseudoscience. When the photon returns to its original state, entropy does not decrease in the universe as a whole. The photon's local entropy decreases, but the measurement apparatus, the laser, the laboratory, and everything else involved in the experiment, the second law remains intact. This principle was anticipated over a century and a half ago by a thought experiment. In 1867, James Clerk Maxwell imagined a tiny intelligent being, later named Maxwell's demon. It could open and close the door to let fast-moving molecules pass into one chamber and slow-moving molecules into the other. It would decrease entropy locally, seemingly violating the second law. The paradox was not resolved until the 1960s. Erasing that information at the end of the process requires energy and generates heat. The demon does not violate the second law. It merely postpones the entropy increase. The photon experiment operates on the same principle. The researchers did not create a net decrease in entropy. They transferred entropy from the photon to the measurement apparatus. The photon's state was restored, but the information about its original superposition was effectively erased from the photon and recorded elsewhere. The universe's total entropy increased, just as the second law demands. The photon got a temporary reprieve from the arrow of time. This brings us to a deeper question that connects this experiment to the most profound puzzles in theoretical physics. Can information be destroyed, or is it truly eternal? This is the same question that ignited the black hole information paradox in the 1970s. If information is destroyed, quantum mechanics is wrong. If quantum mechanics is correct. John Archibald Wheeler, the physicist who coined the term black hole and mentored a generation of giants, took this question to its logical extreme. In the 1980s, he argued that information is not a property of the physical world. Every particle, every field, every force is at bottom a manifestation of binary choices, Universals, yes or no. Matter and energy are derived from information, not the other way around. The photon state was restored because the information needed to reverse its evolution was never truly lost. If information were genuinely destroyed at the quantum level, the reversal would have been impossible. It can be scrambled, but not erased. This has direct implications for the measurement problem. When a quantum particle is measured, the wave function collapses. This collapse has always been treated as irreversible. Once you measure the particle, you cannot return to the superposition. The experiment challenges this assumption. If the photon state can be rewound after it has interacted with the beam splitter, the wave function can, under the right conditions, be reconstructed. The irreversible arrow of measurement may be an illusion born of practical limitations. The many worlds interpretation of quantum mechanics, first proposed by Hugh Everett in 1957, offers a natural framework for understanding this. All outcomes of a quantum measurement occur simultaneously in branching parallel universes. The other branches continue to exist, inaccessible, but real. The 50% probability of successful reversal is not a failure of the experiment. In half the branches, the photon reverses. Both outcomes are real. The transactional interpretation, proposed by physicist John Cramer in 1986, goes even further. An electron emits a wave that travels forward in time to a potential absorber. The interaction is confirmed when these two waves form a standing wave across space-time. The particle has moved from emitter to absorber, but the communication between them was instantaneous across time. It is a direct observation of the backward-in-time component that Cramer predicted 40 years ago. The experiment has strict limitations that prevent any practical time travel. You cannot guarantee that the photon will rewind. More importantly, the reversal is local to the photon's internal state. You cannot encode a message in the photon and have it arrive before you sent it. The photon's evolution is reversed. No causal loops are created. No grandfather paradoxes emerge. The distinction is subtle but critical. Time reversal in quantum mechanics is not the same as time travel in science fiction. It is the restoration of a quantum state to an earlier configuration, not the physical transport of an object. It simply returns to a state that is mathematically identical to its earlier state. The arrow of time for the photon's internal degrees of freedom briefly points backward. This limitation is not a disappointment. The experiment demonstrates that the fundamental laws of physics are more flexible than we assumed. It is a physical reality that can be observed and manipulated. It is a statistical tendency. For a single photon, for a human being, it is insurmountable. But the fact that the barrier exists at all, and that it can be crossed by a single particle, changes how we think about the nature of time itself. The experiment forces us to ask a question that has no comfortable answer. If time is not fundamental, if the arrow of time is merely an emergent property of large systems, is it a dimension like space, as Einstein taught us? Or is it something else entirely? The experiment does not answer these questions. The universe is not only stranger than we suppose. The photon on the beam splitter does not know whether it is moving forward or backward in time. It simply exists, a packet of probability and information, indifferent to the direction of entropy. The arrow of time is our problem, not its. We are the ones who remember the past and anticipate the future. For the photon, time is symmetric. For us, time is a river that flows only one way. The experiment does not change that. But it reveals that the river is not a law of nature. It is a perspective. And perspectives can shift. The philosophical question that emerges from this experiment is not merely academic. If time is not a fundamental feature of the quantum world, if a single photon can have its state rewound without violating any law of physics, then what exactly is time? It is not woven into the fabric of reality at the deepest level. It arises from the interactions of countless quantum systems. A single molecule does not have a temperature. Temperature is a statistical property of large collections of molecules. Similarly, time may be a statistical property of large collections of quantum events. The arrow of time, the distinction between past and future, it is real for us, but it is not fundamental. In the 1980s, the physicist Don Page, a former student of Stephen Hawking, explored the possibility that time emerges from the entanglement between quantum systems. That reference frame can be interpreted as time. The photon experiment does not prove Page's hypothesis, but it is consistent with it. The photon on the beam splitter, it is only when the photon interacts with a measurement apparatus, when it becomes entangled with the laboratory, that the arrow of time asserts itself. The legacy of this experiment places it in a long and distinguished line of quantum demonstrations that have fundamentally altered our understanding of reality. That single experiment launched the quantum revolution. In 1982, Alain Aspect and his team in France demonstrated that quantum entanglement is real. Aspect's experiment closed the door on any hope that quantum mechanics could be explained by hidden variables. In 1999, Anton Zeilinger and his group in Vienna performed a delayed choice experiment that showed a single photon could retroactively decide whether to behave as a particle or a wave. This experiment suggested that the act of observation could, in a sense, reach backward in time. It does not overturn quantum mechanics. It demonstrates that the time symmetry inherent in the Schrödinger equation is not a mathematical abstraction. Each of these experiments forces us to revise what we mean by reality. The Aspect experiment taught us that the universe is non-local. The Zeilinger experiment taught us that the future can influence the past. And now, this experiment teaches us that time itself is not the rigid framework we once believed. The next question is scale. Can two entangled photons be rewound together? If two photons share a quantum state, can that joint state be restored to an earlier configuration? This would be a significant step beyond the single photon experiment. It would demonstrate that time reversal is not limited to isolated particles, but can apply to correlated systems. Entangled photons are more fragile than single photons. Their quantum states decohere more rapidly when interacting with the environment. Maintaining the coherence needed for a successful reversal over two particles requires exquisite control over the experimental conditions. If two entangled photons can be rewound, it would suggest that the time symmetry of quantum mechanics extends to multi-particle systems. Beyond two photons, the next frontier is small molecules. Could a simple molecule? In 2023, a team at the University of Vienna demonstrated that they could create quantum superposition states. They are complex structures with internal degrees of freedom. If a molecule of that size can be placed into a superposition, the answer is not yet known. The probability of successful reversal drops exponentially with the number of particles. For a molecule with 1,000 atoms, the chance of spontaneous reversal is astronomically small. But with active intervention, with the correct inverse operations applied by a carefully designed apparatus, the probability may be higher than natural chance. The experiment has not been done. The theoretical framework suggests it is possible. The engineering challenge is formidable. The connection to quantum computing. Quantum computers operate by manipulating quantum states, superpositions, and entanglement to perform calculations that are impossible for classical computers. Quantum states are fragile. They interact with their environment, lose their coherence, and introduce errors. Every quantum computing research group in the world is racing to develop error correction techniques that can detect and fix these errors before they corrupt the calculation. If a quantum state can be restored to an earlier configuration, then a quantum computer might be able to undo its own errors. Instead of detecting an error and then applying a correction, the quantum state would be returned to its pre-error configuration, preserving the information that would otherwise be lost. Quantum error correction is one of the most active areas of research in physics and computer science. The current state of the art as of 2026. The surface code, developed by physicists at Google and IBM, requires hundreds of physical qubits to represent a single logical qubit. A rewinding-based approach could potentially reduce this overhead by allowing the computer to reverse its own evolution when an error is detected. This is speculative. The engineering challenges are significant. But the theoretical possibility is real. The photon experiment also has implications for the foundations of thermodynamics. If quantum states can be rewound, then the second law is not a barrier to certain kinds of information processing. The Landauer limit, which states that erasing a single bit of information requires a minimum energy expenditure, is based on the assumption that information is destroyed when it is erased. But if a quantum state can be restored to an earlier configuration, the information is not destroyed. The energy cost of erasure may be avoidable if the state is rewound rather than erased. But it suggests that the Landauer limit is not a fundamental bound on computation. Other methods may be more efficient. The deeper question, the one that keeps physicists awake at night, is what this all means for our understanding of causality. If the fundamental laws of physics do not care about the direction of time, then cause and effect lose their absolute status. The delayed choice experiments have already demonstrated this. A measurement decision made after a photon has entered an interferometer. The future determines the past. The photon rewinding experiment takes this one step further. It demonstrates that the evolution of a quantum system can be reversed. The system can return to a state that existed before the interaction occurred. The arrow of causality is not a law. It is a statistical tendency that emerges in large systems. This raises a question that is as much philosophical as it is physical. If causality is not fundamental, if the future can influence the past, then the distinction between choice and destiny collapses. The universe becomes a single block of space-time, where every event is equally real, equally present, and equally connected. The past is not gone. The future is not yet to be determined. Both exist simultaneously in the four-dimensional manifold of space-time. Our experience of time as a flowing river is an illusion generated by the way our brains process information. The universe, at its most fundamental level, is static. Everything that ever happened, or will happen, is already there, encoded in the quantum state of the cosmos. This is not a new idea. Einstein himself believed in the block universe. He wrote to the family of his friend Michele Besso, after Besso's death in 1955, saying, "People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. The photon state can be rewound because the distinction between past and future is not fundamental. The experiment simply accesses a different slice of that block. The final question, the one that has no answer in any textbook. If time is an illusion, then the subjective experience of time passing, the feeling that moments flow from past to future, It is the foundation of every human experience. How can our brains construct a linear narrative of time if the universe itself does not have one? It is a question that physics cannot answer alone. It requires a synthesis of physics, neuroscience, and philosophy. The photon experiment does not solve this problem.